You probably think the nearest star to us should feel reassuring. I mean, if you had to point to one place in the entire galaxy that might someday matter to humans beyond Earth, it would be the one right next door, wouldn't it? That quiet point of light in the southern sky, too faint for your eyes to notice, sitting just 2 light years away, astronomically speaking. That's practically within reach. That star is Proxima Centauri, and for a long time it was nothing more than a name in a catalog, a dim companion to the brighter Alpha Centauri pair. Something astronomers noted and then moved past, because it didn't seem to offer much of anything at all. But then something changed, and I want you to feel the shift the same way scientists did, because it didn't happen gradually. It happened all at once. In 2016, after decades of staring, measuring, doubting, and refining instruments to absurd precision, a team finally saw the tiny wobble of this star and realized it wasn't alone, that something was tugging on it. Something with mass, something real. That something became known as Proxima b, a rocky world, roughly the mass of Earth, orbiting right inside what we like to call the habitable zone, the narrow band of distance where temperatures might allow liquid water to exist. And the moment that discovery landed, everything changed, because suddenly the closest star to us wasn't just a point of light anymore. It was a destination, a candidate, a place you could imagine standing on, looking up at a dim red sun hanging in the sky. You can almost see how the story writes itself from there, can't you? Humanity, after centuries of looking outward, finally finding a world within reach that might not be entirely hostile. A place where water could pool, where chemistry might resemble something familiar, where the first fragile steps beyond the solar system might someday land. It's the kind of idea that spreads fast, not just through scientific papers, but through imagination. Because once you say Earth-sized and habitable zone in the same sentence, people don't hear the uncertainty. They hear possibility. And possibility is a powerful thing. Now here's where I want you to slow down with me, because this is the part where your intuition, your very human instinct to connect dots too quickly starts to get you into trouble. The phrase habitable zone sounds comforting, almost like a guarantee. But it's not a promise. It's a condition, a single requirement in a long chain of requirements. And meeting one of them doesn't mean the others are satisfied. You can have the right distance and still have the wrong everything else. And nature doesn't care about how hopeful the label sounds when it hands you that classification. What made Proxima Centauri so compelling wasn't just that it had a planet, but that it seemed to check that one crucial box. And because it was so close, closer than any other known star, it became more than a discovery. It became a projection screen for everything we wanted to find out there. Every assumption about life beyond Earth compressed into a single system we could actually study in detail. Instruments improved, models sharpened, and suddenly this faint red dwarf wasn't an afterthought anymore. It was a laboratory, a place where one question could finally be pushed harder than anywhere else. Can a world around a star like this really support life? And for a brief moment, before the data started to pile up, before the deeper physics began to assert itself, before the star revealed what it was actually like, that answer felt like it might be yes. Not because we had proof, but because we had just enough evidence to let the idea take hold, and once it did, it became very difficult to let go. Now, once you've allowed yourself to believe that a nearby star might host something like Earth, it becomes surprisingly easy to fill in the missing details without even realizing you're doing it. Because the phrase Earth-sized planet in the habitable zone doesn't just describe a measurement, it triggers a picture in your head. And I want you to notice that picture very carefully because it probably looks familiar. Oceans, clouds, maybe a dim red sun hanging low in the sky. A world not so different from the one you're standing on right now. That world is Proxima Centauri b, and the moment it was announced, that image spread everywhere. Not because it was confirmed, but because it was plausible enough to imagine, and once something is imaginable, it starts to feel real long before it actually is. The logic seems straightforward on the surface, and that's exactly why it's so dangerous. If a planet orbits at the right distance from its star, then temperatures might allow liquid water to exist. And if liquid water can exist, then chemistry has a chance to become biology. And if biology has enough time, it might become something more complex. It's a chain of reasoning that works beautifully when you apply it to Earth. So naturally, you try to extend it outward. And suddenly, Proxima b starts to look less like a distant object and more like a candidate, a possibility, almost an inevitability, waiting to be confirmed. But what you're really doing there is compressing a huge number of unknowns into a single familiar outcome. And physics doesn't reward that kind of shortcut, because the habitable zone is not a place where life exists. It's a place where one specific condition temperature might be right under ideal circumstances. And those circumstances depend on everything else about the system behaving in ways that are, more often than not, far from ideal. You need an atmosphere, not just any atmosphere, but one with the right composition and pressure to regulate heat and protect the surface. You need a magnetic field strong enough to shield that atmosphere from being stripped away. You need geological activity to recycle materials and stabilize long-term climate. You need stability over billions of years, not just moments of temporary balance. And every one of those requirements sits on top of the others, forming a structure that is much more fragile than the simple phrase habitable zone suggests. Now here's the part where things begin to shift, and it's subtle at first, almost easy to miss. If you're still holding on to that initial picture, Proxima Centauri is not like the Sun. It's a red dwarf, much smaller, much dimmer, emitting only a tiny fraction of the energy our star produces, which means that for Proxima b to receive enough warmth for liquid water, it has to orbit incredibly close to its star, far closer than anything in our solar system except Mercury. And even that comparison doesn't quite capture how extreme the situation is. We're talking about a world that completes an orbit in just over 11 days. A world that sits so near its star that the distinction between day and year starts to blur in ways your intuition isn't prepared for. And yet, at this stage, you could still argue that none of that rules life out. Not definitively, because nature has a way of surprising us, and there are theoretical models suggesting that under the right conditions, even a planet this close could maintain regions where temperatures remain moderate, especially if it possesses a thick atmosphere capable of redistributing heat from one side to the other. It's the kind of idea that keeps the hope alive just enough to justify looking deeper, to justify building better instruments, running more detailed simulations, asking more precise questions. But if you look closely at what's happening here, you'll see that the story has already started to lean on assumptions, each one compensating for something that doesn't quite fit, each one stretching the idea of habitability a little further than before. And the more you stack those assumptions, the less you're describing a likely world, and the more you're constructing a possibility. That depends on everything going right in a system that has given you very little reason to expect that it will. If you keep following that line of reasoning, staying honest with the physics instead of the picture in your head, you eventually run into a consequence that isn't dramatic at first glance but becomes impossible to ignore once you really sit with it. And that is what happens to a planet when it orbits this close to its star for long enough. Gravity does not just hold things in orbit, it reshapes how they move, how they rotate, how they experience time itself. And in the case of Proxima Centauri b, that gravitational interaction almost certainly leads to tidal locking. A state where the planet's rotation period matches its orbital period so perfectly that one side always faces the star while the other side never does. Now, I don't want you to just understand that as a definition. I want you to actually place yourself there, because this is where the abstract idea of a habitable world starts to fracture into something much harder to reconcile. Imagine standing on the surface and looking up, except the sky never changes. The star never rises or sets. It just hangs there, fixed, unblinking, pouring energy onto the same hemisphere day after day. Year after year, without interruption. There is no cycle to regulate temperature, no night to allow the surface to cool, no shifting pattern of light to distribute energy across the globe. Everything is locked into place. On the opposite side of the planet, the situation is just as extreme, but in the other direction, a permanent night that never sees the star at all, a region where heat is not replenished, and whatever warmth exists must come from the slow, inefficient transfer of energy through the atmosphere or the ground. If such pathways exist at all, over time, the contrast between these two hemispheres becomes enormous. And we are not talking about a mild difference. We are talking about temperature gradients that could span hundreds of degrees, enough to create an environment where one side is relentlessly heated while the other approaches deep freeze conditions. You might be tempted to rescue the situation at this point, to say that perhaps a thick atmosphere could smooth things out, carrying heat from the day side to the night side, creating a more temperate region somewhere in between. A band around the planet where conditions are neither too hot nor too cold, a kind of perpetual twilight zone where liquid water might still exist, and that idea is not unreasonable. It shows up in serious scientific models, and under certain assumptions it can work, at least on paper. But notice what has to be true for that to happen, because now you are relying on an atmosphere that is not just present, but dense, stable, and efficient at redistributing energy across a planet that is otherwise locked into an extreme configuration. And even if you grant all of that, even if you allow for a narrow region where temperatures fall into a tolerable range, you are still dealing with a world that is fundamentally divided, not just geographically but physically, where most of the surface exists in conditions far removed from anything we would call Earth-like, and where the habitable region, if it exists at all, is not a global environment, but a thin, precarious boundary between two extremes. It is a place defined less by what it has and more by what it barely avoids. So the image you started with, the one with oceans and clouds spread across a familiar world, begins to collapse into something far stranger. A planet where survival, if it is possible, would be confined to a narrow strip circling the globe, a region balanced between fire and ice, where the difference between livable and lethal is measured not in continents or climates, but in distance from a line that never moves. If the story ended with tidal locking, you could still argue that life might find a way, because life is remarkably good at adapting to gradients, to edges, to those narrow regions where conditions are just barely tolerable. But the problem is that the star itself refuses to remain a passive source of light and heat. And this is where Proxima Centauri reveals a behavior that changes everything. It is not stable in the way our sun is stable. It is not calm in the way you might expect from something so small and dim. It is volatile, magnetically tangled, constantly building up and releasing energy in violent bursts that we call flares, and on this star, those flares are not rare events. They are a defining feature of its existence. Now, I want you to think about what a flare actually is. Not just a flash of light, but a sudden release of enormous amounts of energy across the electromagnetic spectrum, including ultraviolet and X-ray radiation. The kinds of radiation that interact directly with molecules, that break chemical bonds, that damage biological structures at the most fundamental level. On Earth, we are largely shielded from this by distance and by our atmosphere, which absorbs much of that high-energy radiation before it can reach the surface. But on a planet like Proxima Centauri b, sitting so close to its star, that protection becomes much harder to maintain even under ideal conditions. In 2016, observations captured something that forced astronomers to take this seriously in a new way. A superflare from Proxima Centauri that increased the star's brightness dramatically for a short period of time, releasing an amount of energy that, when translated to the distance of Proxima b, meant that the ultraviolet radiation hitting the planet's surface could reach levels far beyond what even the most radiation-resistant microorganisms on Earth can tolerate, not marginally higher, not something life could potentially adapt to over time, but orders of magnitude beyond lethal thresholds, delivered in bursts that last seconds or minutes, but carry consequences that extend far longer. And if this were a rare occurrence, something that happened once every few thousand years, you might still find a way to argue around it, to imagine that life could retreat, recover, rebuild in the long intervals between such events. But that is not the environment this star creates. Proxima Centauri produces these powerful flares frequently, with smaller flares occurring even more often, creating a radiation environment that is not defined by occasional extremes, but by persistent instability. A background condition where the surface is repeatedly exposed to pulses of high-energy radiation with little time to recover in between. Now consider what that does to an atmosphere, because even if you had one, even if you assumed that earlier conditions somehow allowed a substantial envelope of gases to form around the planet, those flares would drive complex photochemical reactions, breaking apart molecules, depleting protective layers like ozone, and allowing even more ultraviolet radiation to penetrate to the surface. Over relatively short time scales, measured not in billions of years, but in thousands or even less, the shielding effect of that atmosphere could be significantly reduced, transforming what might have been a partially protected environment into one where radiation reaches the ground with increasing intensity. So when you picture standing on that twilight band in that narrow region where temperatures might otherwise be tolerable, you have to add another layer to the scene, because the sky above you is not just a dim red glow. It is a source of intermittent, unpredictable violence, flashes of energy that sweep across the planet, altering the chemistry of the air, striking the surface with radiation levels that do not merely challenge life, but actively dismantle it at the molecular level. And they do so not once, not rarely, but often enough that stability, the one thing life truly depends on, never has the chance to take hold. Even if you tried to argue that life might endure those bursts of radiation, that somehow chemistry could retreat beneath the surface or evolve mechanisms to survive the intermittent violence, there is another process unfolding in parallel, quieter, less dramatic, but far more relentless, and it does not come in flashes or spikes. It is continuous, persistent, and fundamentally destructive over long time scales. This is the stellar wind, a stream of charged particles flowing outward from Proxima Centauri And unlike the flares, which arrive in sudden bursts, this wind never really stops. You are already familiar with the idea, whether you realize it or not, because our own sun produces a stellar wind as well. And on Earth it gives rise to auroras when those charged particles interact with our planet's magnetic field, creating those shifting curtains of light near the poles. But what makes that possible? What allows those particles to become something beautiful rather than destructive? Is distance and protection. Earth sits about 150 million kilometers away from the sun, and it is wrapped in a magnetic field generated by its rotating, convecting core, a field that deflects most of the incoming particles, guiding them around the planet instead of letting them slam directly into the atmosphere. Now take that picture and start removing the safeguards one by one. Move the planet much closer to its star. Reduce the distance until the flow of particles becomes far more intense. Increase the density and pressure of that wind, and then weaken or eliminate the magnetic field that would otherwise serve as a shield. That is the environment faced by Proxima Centauri b, a world that orbits roughly 20 times closer to its star than Earth does to the sun, where the stellar wind is not just stronger, but potentially thousands of times more forceful at the orbital distance of the planet. And here is where the process becomes especially important, because the stellar wind does not need to destroy the atmosphere in a single event to be effective. It works by erosion, by gradually transferring energy to atmospheric particles, heating them, accelerating them, allowing lighter elements like hydrogen to escape the planet's gravitational pull, and in the process dragging heavier elements along with them. This is not a catastrophic stripping that happens overnight. It is a slow peeling away, a continuous thinning that over millions and billions of years can transform a once substantial atmosphere into something tenuous, or even remove it entirely. If the planet lacks a strong magnetic field, and tidal locking makes that a very real possibility by slowing or even halting the internal dynamo that would generate such a field, then the stellar wind can interact directly with upper layers of the atmosphere, compressing it, energizing it, and steadily carrying it off into space. Each particle lost is insignificant on its own. But the process does not stop, and the cumulative effect becomes unavoidable. You do not notice the loss from one moment to the next. But over geological timescales, the difference is absolute. And while this is happening, the star continues to emit high levels of X-ray and extreme ultraviolet radiation, further heating the upper atmosphere and making escape even easier, so that what you have is not one mechanism working in isolation, but multiple processes reinforcing each other, all pushing in the same direction. The flares weaken the atmosphere's protective chemistry, the radiation heats it, and the stellar wind carries it away, step by step, layer by layer. So when you think back to that earlier assumption that perhaps a thick atmosphere could redistribute heat and create a habitable zone along the twilight band, you have to confront the fact that such an atmosphere is not something you can simply assume into existence and then leave unchanged, because in this environment it is under constant attack. Not from a single dramatic event, but from a steady, unending flow that does not pause, does not diminish, and does not give the planet time to recover what it loses. At this point, you might be tempted to focus everything on a single world and ask whether, under some unlikely combination of conditions, it could still hold on to the ingredients for life. But the moment you widen your view just a little and look at the entire system around Proxima Centauri, a different pattern begins to emerge. One that is much harder to explain away as bad luck or incomplete data, because Proxima b is not alone, and what we see when we examine its neighbors is not a range of possibilities, but a set of constraints that seem to close off every direction you might try to go. Take Proxima Centauri, D. For example, a much smaller world, roughly a fraction of Earth's mass, orbiting even closer to the star than Proxima b, completing a full orbit in just a few days at a distance so tight that the distinction between planet and environment starts to blur under the intensity of the radiation it receives. At that proximity, the equilibrium temperature alone pushes conditions far beyond the range where liquid water could exist on the surface under any reasonable atmospheric scenario. And whatever environment might exist, there is subjected to the same flares, the same stellar wind, the same relentless bombardment, only amplified by the shorter distance. If Proxima b stands too close to a fire, Proxima d is effectively inside it. So you shift your attention outward because that is the natural move. You look for a region farther from the star where the intensity drops, where the radiation environment becomes less extreme, where perhaps a planet could retain an atmosphere long enough for more stable conditions to develop. And there, in that outer region, you find Proxima Centauri, a more massive world orbiting at a much greater distance, where the pressure from the stellar wind is thought to be comparable to what Earth experiences from the sun on paper. This sounds promising, because the destructive forces that plague the inner planets are reduced, and the environment begins to look more familiar in terms of particle flux and long-term stability. But distance solves one problem by introducing another, because Proxima Centauri is an intrinsically faint star emitting only a small fraction of the energy of our sun, which means that by the time you move far enough away to escape the worst of the stellar wind and radiation, you have also moved far beyond the region where temperatures could support liquid water. At the orbit of Proxima c, equilibrium temperatures plunge to levels where any surface water would be frozen solid, locked away in ice, with no obvious mechanism to maintain a stable liquid phase over geological timescales. So now you are left with a system that seems to offer you a set of choices, but every choice comes with a trade-off that undermines the very condition you are trying to satisfy. Move inward, and you gain warmth at the cost of atmospheric stability and radiation exposure. Move outward, and you gain stability at the cost of temperature, freezing out the very chemistry you need. There is no obvious middle ground, no region where all the necessary factors align at once, no orbit where distance, radiation, atmospheric retention, and thermal conditions come together in a way that resembles what we know to be conducive to life. And what makes this especially difficult to reconcile is that the system itself is not unusual in any exotic sense. It follows the rules, we understand. It behaves according to the same physical principles that govern stars and planets throughout the galaxy, which means that what you are seeing here is not an outlier, but a consequence. Not a failure of this particular system, but a demonstration of how these systems tend to work when you look closely enough. If this were just a story about one inconvenient star and a handful of unfortunate planets, you could set it aside as an interesting case study, something to refine models against and then move on from. But the reason this system matters so much is that it is not rare, not unusual, not some exotic corner of the galaxy behaving badly. It is representative of the most common kind of star that exists. Red dwarf stars make up roughly 3/4 of all the stars in the Milky Way, which means that whatever pattern you see here is not confined to a single nearby system. It scales outward across tens of billions of worlds. For years, that statistic was a source of optimism, because if most stars are red dwarfs, and many of them host rocky planets within their habitable zones, then the galaxy should be filled with opportunities for life, an enormous inventory of potential Earth-like environments waiting to be explored. It was a simple multiplication of probabilities that led to a comforting conclusion. More stars of this type means more chances for biology to emerge, but that conclusion quietly assumed that the habitable zone around a red dwarf functions in the same way it does around a star like the Sun. And that assumption is exactly what systems like Proxima Centauri are forcing us to re-examine. Because when you combine everything, we have walked through the tidal locking that divides a planet into extremes, the constant flaring that floods it with high-energy radiation, the stellar wind that strips away its atmosphere, the early evolutionary phase that may remove water before stability is even possible. You do not get a marginal environment that might or might not support life. You get a system that systematically removes the conditions life depends on, one layer at a time. And if that pattern holds, even in a significant fraction of red dwarf systems, then the sheer number of planets in habitable zones stops being reassuring and starts becoming misleading. Observations are beginning to reinforce this shift in perspective. Studies of other red dwarf systems, such as TRAPPIST-1, have revealed planets that appear to lack substantial atmospheres altogether, suggesting that the processes we infer from Proxima Centauri are not isolated events, but recurring outcomes. The instruments are improving, the data is accumulating, and instead of uncovering a hidden abundance of Earth-like worlds, we are finding repeated signs of environments that struggle to hold on to the very features that make Earth what it is. Now, this does not mean that life cannot exist around red dwarfs under any circumstances, because nature is rarely absolute in that way, and there are still scenarios being explored, possibilities involving thick atmospheres, subsurface oceans, or planetary histories that deviate from the simplest models, but each of those possibilities requires a chain of favorable conditions that must all align despite a background environment that is actively working against them. And the more conditions you have to assume, the less likely it becomes that they are commonly met. So the role of Proxima Centauri shifts from being a candidate destination to something more instructive, almost cautionary, because it offers us a system close enough to study in detail, clear enough to analyze with multiple instruments, and harsh enough to reveal what red dwarf environments can do to their planets over time. It is not just telling us about itself, it is giving us a framework for interpreting a vast population of worlds that we cannot yet observe with the same clarity. And when you step back and look at the broader picture, the implication is not that life is impossible in the universe, but that it may be far more selective than we once hoped. That the conditions we take for granted on Earth are the result of a very particular balance, one that is not easily reproduced, even in places that at first glance seem perfectly positioned to allow it.